Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 13, isomers. Okay, isomers are two or more compounds with the same chemical formula, okay, but a different arrangement of atoms in the compounds. This could be an arrangement of structure or of 3D space or orientation, which we'll get to the differences here in a second. Isomers that are different isomers will have different properties, because let's say I have butane here and I change it to methyl propane. These, even though they're isomers of each other, they have different properties because of the shape. Okay, the shape has everything to do with properties in chemistry. And you'll actually learn later that this has a higher boiling point, for example, than this guy because of the way it's shaped. But they have the same chemical formula. So the main difference is the main isomers that you'd want to know are constitutional and stereoisomer. Now there are subtypes of stereoisomers that we're going to get into here in part C, but you'll want to know the main difference between these guys. So a constitutional, also known as structural isomer, literally means that you're changing the bonds around it. So let's say I have AX2, so I could have AXX, or I could have XAX, right? These are constitutional isomers of each other because the bonding is different, okay? Now, if it was a stereoisomer, we would have to have this. Let's say it's XAA, okay, or XAX. But in somehow, there's a different 3D spatial orientation that we can't see yet. Okay, and it's going to be easier once we start talking about diastereomers and enantiomers here in a little bit, what that looks like. So, and then stereoisomer, like we've been saying, it's the same general arrangement of atoms, but with different orientations in 3D space, okay? And a lot of times what we do is we designate 3D space by the following. So if it's just a line, it's going to be, that just means it's flat on the page, okay? But if I draw a dashed line like this, that means going out of the page, okay? And if I draw a wedge like this is coming out of the page, okay? So this is kind of how in chemistry we draw 3D structures. We say this is coming out of the page, that's going into the page. And that kind of helps us tell 3D arrangements on a 2D paper, right? So now there are 3 types of stereoisomers that you're going to want to know. One is called a diastereomer, one is called an enantiomer, and another one's called a geometric isomer, also known as cis and trans isomers, which we'll get to here in a second. But quick definition on both of these. So enantiomers are non-superimposable mirror images, whereas diastereomers are non-superimposable non-mirror images, and I'll show you the difference here in a second. So take your left hand and face it towards your right hand. This is obviously not going to be a great drawing. Here's the mirror, and you'll notice that when they're facing each other, they look identical, okay? But once you try to superimpose one on the other, if I flip my right hand around and try to put it on top of the other, you'll notice that you get a little turtle, right? You get thumbs on both sides which means that they are non-superimposable, okay? But they're mirror images of each other, and so your hands are actually enantiomers, okay? Enantiomers are non-superimposable mirror images, and in chemistry, what these look like is the following. If you look right here, okay, I'm going to be zooming in here. I've got a carbon bound to a hydrogen, bromine, fluorine, and chlorine. And this dash, it's not very, the quality is not very good here, but this is supposed to be a dash, which looks like this, okay? So a dash, when we're drawing these, in 3D space, it's kind of hard to tell. So what we do is we say this is going into the page, and then this wedge here is coming out of the page, okay? So for just know that this is a dash here, and this is a wedge, okay? And that'll be the same on this side. So notice the mirror here, okay? And you'll see that carbon is bound to the same 4 groups, and that it even looks like itself, right? But if you can do this in your mind, rotate this, and I'm gonna draw the product down here, what that would look like. So I'm gonna put carbon up here. I'm gonna put the hydrogen and the bromine in the back, okay? Because these are just on the plane of the page, so I'm going to flip those. And then you'll notice that fluorine, which was going into the page, once you rotate this, it now comes out of the page, okay? And then same with chlorine. Chlorine, which was coming out of the page, is now getting into the page once you rotate it that way, okay? So now I'm going to draw this here. And notice that these end up on different ends, right? Which means it's a mirror image of itself, but it's a non-superimposable mirror image. So this is what we call an enantiomer, and then it's an enantiomer because of what we refer to as this chiral center. Okay, chiral centers are areas where we have these kinds of properties where we cannot superimpose certain parts of the molecule on themselves. So a chiral center is where, for the sake of this class, you'll want to just know that a chiral center, also known as a stereogenic center, you actually may hear that more often once you get into later chemistry, but it's pretty much the same thing, okay? Chiral centers and stereogenic centers, where in 3D space, the 3D spatial arrangement matters. And the only way, for the sake of this class, just know that it's an atom bound to 4 elements, or 4 plus groups, okay? Now, 4 plus, I mean 4 plus different groups. So let me put different here. Okay, they have to be different groups, not 4 just groups in general. So notice that this carbon was bound to 4 different groups. It was bound to a hydrogen, bound to a bromine, bound to a fluorine, bound to a chlorine. If this had been a chlorine, for example, that would be 2 of the same, right? And so this would be 1, 2, 3 different groups. So 4 plus different groups is what you want to look for when we're looking at a chiral center. And when we look at a chiral center, generally especially in organic chemistry, you'll always see these dashes and wedges in the structures because they actually have to designate those. They will change the properties. In fact, a lot of our hormones have enantiomers, enantiomeric forms, or diastereomeric forms. And if we were to use those forms, they actually would not function. Okay, and so it's really important, the shape, the 3D arrangement that we were talking about earlier. So diastereomers, an important part about diastereomers is they're almost like enantiomers, except the definition can be kind of confusing because it's a non-superposable, non-mirror image. So you're like, well, that means nothing then, right? Non-mirror image, if it's, I don't even know what that's supposed to look like, and it's a non-superposable. Let me show you what I mean. So for a diastereomer, you have to have at least 2 plus chiral centers for you to even have a diastereomers. Okay, so let me give you the example of this. Hopefully you understand the stick structure in organic chemistry. I'm going to put a bromine here and then a chlorine here. Okay, in organic chemistry, at every bend is a carbon. Okay, like this. And where it's not shown, you're going to assume that there's hydrogens to saturate the carbon. So here we'd say, okay, there's 3 hydrogens here because I know it's bounding. It can make 4 bonds and it's already bound to one of these, this carbon over here. This carbon is already bound to a carbon here, and a bromine there. So I'm just going to assume that there's a hydrogen coming out of the page here, or a hydrogen going into the page here, or 3 hydrogens here. Okay, that's just a quick rundown of that. Hopefully you can kind of see that in the structures that we'll be drawing here. So here's my structure. It's got 2 chiral centers. You'll notice that the bromine here is going out of the page, going into the page, and then chlorine here is coming out of the page. If I were to draw the mirror image of this guy, it would look like this. Okay, this would be the enantiomer, because when you flip this around, I'm going to rotate this. Okay, when I rotate that, I'm going to get the following. So notice that both of my stereogenic centers, my chiral centers, are flipped, right? They're exactly the opposite. That is the definition of an enantiomer, is where every chiral center is flipped, okay? But in a diastereomer, okay, let me actually note that down here. All chiral centers are flipped. Whereas in a diastereomer, the reason you need 2 is because you only need to change one of them, or one or more, but not all of them. Okay, so let's say I drew instead a wedge here for this bromine. Okay, notice that it's no longer a mirror image. That's what we mean by non-mirror image. So it looks relatively the same, but in 3D space, this bromine is now coming out of the page where it was going into the page here. So it's not a mirror image, but it has the same chiral centers. And when I flip this around, instead of going out of the page now, it's going to go back into the page. Okay, and notice that that at least one of them is the same, right? This is the same here, but we don't have the same here. So they're non-superimposable, and they're not mirror images. And so a diastereomer, let me note down here, diastereomer is 1 plus chiral centers are flipped. Okay. But notice that it cannot be all of them. If it was all of them, then it would be an enantiomer. Not all. Okay. So that's the main difference between an enantiomer and a diastereomer. And there is a subtype of diastereomers that we will touch on briefly here in a second, which are called cis and trans isomers. But hopefully you were able to get this idea of what a chiral center is, because that's going to be critical to understanding whether something will be an enantiomer, a diastereomer, and what it should look like in 3D space. And just remember that a chiral center here is where an atom is bound to 4 different groups, and it's typically carbon, okay, because carbon can make 4 bonds, and it has to be 4 different groups. So if you have 2 chlorines or something, it's not going to work. We'll go through more examples in this problem set that hopefully will clarify that concept. All right, so there's this diastereomer called a cis and trans isomer, which are also known as geometric isomers. Geometric isomers have to do with alkenes. Alkenes are double bonds, okay? Now, the reason that we have to designate that is because on a single bond, once we get into hybridization theory, or like valence bond theory, this will start to make a lot more sense. But let's say I'm going to draw sp2 orbitals. You don't know what this is yet, but don't worry, you will in a little bit. This is going to create my single bond, okay? In a double bond, remember, in a double bond is what we call a pi bond. A pi bond is made by unhybridized p orbitals. So here's one p orbital on this atom. Here's another p orbital on this atom. And what happens is these, instead of overlapping on the internuclear axis like sigma bonds do, they overlap above and below or on the sides of bonds. And so what happens is when you have a double bond like this, it actually locks it in place, because before this was free rotating. Any single bond, it can rotate around its axis, but the second you put a double bond in there, it actually locks it in place. And so this, let's say these there had been other hydrogens here. These would be the same molecule actually if there had been hydrogens here, because they have the same chemical makeup. But once we put this double bond here, it now locks these groups on either side of the bond in different ways. So let me show you what I mean. I'm going to cut this bond perpendicularly first. Okay, I'm going to label 2 sides, 1 and 2. And then on side 1, I'm going to determine the biggest group by atomic weight. Okay, so carbon is obviously bigger than hydrogen, so I'm going to circle that. Again, over here, carbon is bigger than hydrogen, so I'm going to circle that. Now, when I look across the bond parallel to it, I'm going to actually say, okay, are they on the same side of each other on this bond, or are they on opposite sides? If they are on the same side, if the biggest groups on this double bond are on the same side as each other, we call it a cis isomer. If they are on opposite sides, okay, if I cut it perpendicularly first, label side 1, side 2, here's my big group here, here's my big group here, and then look across the double bond, notice that they're on opposite sides of each other, so I say trans, okay? And so we have to designate between these. Why? Because they are locked in these positions because of the double bond, okay? If these have been single bonds, these would be the same molecule, but because they are locked in place, they by default end up being different and have different properties. So that's kind of a quick rundown of those types of isomers. Now, we're going to do a lot of examples, and I hope this will kind of clarify it more for you as we go through these. So now, they're asking to draw all constitutional isomers of butene. Now, they have not taught you how to name organic molecules and compounds, so don't worry about memorizing that. Just look it up. Butene, if you don't know, is C4H8, okay? Which means, you wouldn't know this rule, but it actually means that there's a double bond, or a degree of unsaturation is what we call. So I'm going to draw a typical butene. So this is actually called 2-butene. It would actually be called trans-2-butene because this is the trans version of butene. So this is the trans isomer. Okay, I'm going to label it trans. Okay, and it's C4H8. You'll notice that there's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Okay, and then like 4 carbons. Okay. So this is one possible isomer for butene. This happens to be the trans isomer. So you can kind of imagine if I flip this back like this methyl group down, it would look like this. Okay. And now this is going to be my cis isomer because when I look across the bond like this, my biggest groups are on the same side of each other. Okay. Does that make sense? So when we're looking at cis and trans, what you want to do is cut across the bond perpendicularly, and then I just look at each side. This is my biggest group here. This is my biggest group here. Now across the bond, are they on the same or opposite sides? They're on the same side, so I'm going to call it cis. All right. So now we have to figure out other types of butenes, right? I put the double bond here in the middle, but I easily could have put it here on the end, right? Now, a lot of people may be like, oh, well, here's one, and then let me do one on this end too. Notice that these will actually be the same. I'm actually going to put an equal sign here. Okay, equal sign. So don't write these together because they're actually the same molecule, because if you flip this around, it looks exactly like this. Okay, it's just different in a different orientation. So don't make that mistake. A lot of students will actually draw an isomer that's actually identical to an isomer they've already drawn, and they'll actually end up getting some answers wrong. All right, and then there's one more that you could draw here. In fact, so let me just make sure that you don't make this mistake. So I'm going to draw an X like this. And the last one, once you reach max as far as like how many isomers you can do with one parent chain of 4. So we've done parent chains of 4 carbons. So what we do after we've maxed out our opportunities for a particular parent chain, we go down one. So I'm going to make a parent chain of 3, and then I have a methyl group to move around. So I'm just going to put that right here and then make a double bond out of it here. So again, remember, don't make the mistake where you're like, oh, well, this should be a different one. But no, it's just these are the same. Okay, so don't do this. All right, so those are pretty much all the ones that you would have to draw for this one. I don't think there really is any other ones you could draw for butene. So we'll get into more examples on isomers and going through more structural and geometric isomers in problems 3 through 6.